Good morning, everyone. I have kind of a limited home DSL connection, so if nobody minds, I'm going to leave the video off just to preserve some bandwidth. The title of the talk is Optimizing the Navy's Neptune Weather Model for High-Performance Computing Systems. I'm heading up the software engineering and performance engineering effort at the Naval Research Lab Marine Meteorology Division for this particular project, which is to design a new global atmospheric model for the Navy. This would replace the current spectral model called NavGem. That runs at 32 kilometers horizontal resolution operationally. Eventually, Neptune will replace the COEMS regional model. The idea is to have a unified forecasting system for both global and regional forecast capability. The goal for Neptune is to get down to resolutions that explicitly resolve convection on a global scale that's less than 5 kilometers. Running Neptune regionally, we expect to get down to less than 1 kilometer resolution. Neptune is a global atmospheric model in spite of the name, but it's the Navy, so they named it after the god of the oceans, but it is a global atmospheric model. It's spectral element model. It's discretized over a cube sphere domain with three-dimensional spectral elements. It's based on the non-hydrostatic unified model of the atmosphere from Frank Giraldo and his group at the Naval Postgraduate School. The solution at each element is represented by polynomial expansion, the Gauss-Lobato polynomials. The zeros represent the node points. It can be high order. We're currently looking at fourth order polynomials. We could conceivably go up to sixth order. The nice thing about the spectral element, first of all, it's computationally dense, which means that there's good data locality we can exploit. It also entails, for a given resolution, the communication between MPI tasks doesn't increase with numerical order as, let's say, a finite element, or I'm sorry, a finite difference model would. As you increased order, you have to increase the width of the halo communications. Not so with a spectral element model. We have a horizontally explicit, vertically implicit time integrator. There's a new formulation that no longer needs a reference state. And this is all being tested, getting ready for an initial operating capability, that is to replace NavGem and Navy forecast operations in a distressingly short time frame. This is supposed to go operational by 2023. The target resolution for initial operating capability is 8 kilometer quasi-uniform global resolution. We won't have mesh refinement available at that point. That works out to 436 million grid points, node points, spread out over 6.7 million spectral elements. We have to run, in order to be timely for forecasting, we can't take any longer than 10 minutes per forecast day. That's a simulation speed of 144 times real time, that is wall clock time. The resource envelope that we have to fit into is 50,000 cores on the Navy's latest AMD EPIC Rome machine called Narwhale. It's a Cray Shasta, but we'd like to get that down to 35,000 cores to run operationally. So that sort of drives the technical requirements that we have for the model. Computationally, the model has to be efficient and scalable, obviously. We need it to run on both current and future high-performance computing architectures, including GPUs. That also has an influence on making sure the software engineer, or the software is efficient from an engineering point of view. We need to be performance portable over the range of architectures with a single source code, maintainable, extensible, understandable. And that leads to the first major re-engineering we've done of the code over the last year. And that was to redo the the software architecture. We got rid of module data. Everything is now in these Fortran 90 classes. Each of these boxes is a class, and this is the hierarchy. All of the state for the model is stored in the state data for one of these classes. Since it's a hierarchy of classes, we have the child types, pointers to those are actually, they're defined in the class. And there's a back pointer to the parent class so that we can traverse the tree. If you're computing down in a class, you can traverse up to get data from other classes. And then the actual linkages between the class when these are instantiated is done by the create routine, which sets up the pointers. There's also a standard init routine for each class and a standard destroy routine. And then the actual computations are in class specific type-bound procedures. Each class has whatever procedures it needs to do the computations on that class. As we'll see later, that's problematic for OpenACC and OpenMP, which the OpenMP 4.5 and 5 standards claimed that they would support type-bound procedures. It's not clear that that will happen. The standard does, but whether that will be implemented or not. Saying a little bit about the architecture, the main program does not live in the Neptune model. The main program lives in some application-specific driver that then declares and instantiates an instance or one or more instances of the Neptune model type. That driver could be a standalone free forecast driver. It could be the JEDI data assimilation framework that's being developed by an interagency consortium, international consortium, or it could be the Earth System Modeling Framework, the NUOPSI framework to do Earth System type predictions. But in any case, the application will declare and instantiate one or more instances of the Neptune model type, which contains the domain. That in turn contains one or more grids. If it's uniform resolution, it would be a single grid, but we can have multiple grids if we have other refinement levels. The grids in turn, each grid is made up of elements, but the elements are not stored individually, they're stored in blocks. The width of a block can be the width of the vector units on a CPU, the width of a warp on a GPU. On the explicit side, we compute over element blocks. For the implicit solver, we actually compute over blocks of adjacent columns. And again, the width of those column blocks can be adjusted according to the vector characteristics or the fine-grained parallel characteristics of the architecture that we're targeting. That was the software engineering refactoring that we've done over the last year. One of the major other refactorings has been for performance. We've finished a year-long effort to pretty much completely rewrite the Neptune dynamics. That has involved coming up with entirely new data layouts and entirely new loop layouts. The new data layouts are basically engineered to minimize the amount of data that we have to move over the course of a time step. The original baseline Neptune that we started with stored all the global state data in these large continuous Galerkin continuous storage arrays, big global arrays. And then for every element computation, we'd copy out of the arrays into the local data structures for the element, do the computation, and copy back. That had in work we did with the test kernel, the diffusion kernel from the old code, showed that the cost for doing that versus the cost of keeping things element local was about a factor of 4 or 5 for this particular standalone kernel. So right now, the only thing we're using these global storage arrays for is for communication with the outside world in Neptune, for I/O or coupling. But all of the element computations are now done element local. We're working right now on the routine that does the elements compute local solutions, but we have to have a DSS step to compute the global solution. That's still done in these old global arrays. We're in the process of making that a neighbor local computation as well. In terms of the new loop layouts, I presented, I think it was 2 years ago at this workshop, what we were considering. We had this is the one we finally adopted, where the element index is innermost. And so we can compute over multiple elements with the element index being vectorizable on a CPU or a thread parallel on a GPU. The advantage of doing that, having element innermost, and we call this the EPX ordering for no particular reasonable reason. The name just stuck. But the advantage of doing the fine-grained parallelism over the vector, over the element dimension, is that the element dimension is almost completely dependency-free. We have complete control. We can arbitrarily control the width of these element blocks for whatever architecture we're on. So we've done some tests to compare that with the older PX ordering, where the element index was outermost. And it turned out that this was, in fact, more efficient, largely because it allowed us to vectorize more. So between not moving the data around and exposing fine-grained parallelism, we were able to get considerable performance benefits. You'll see that in a couple of slides. And then the last sort of more or less mundane optimization that we've engineered into this refactor code is this let the compiler cook kind of idea. Basically, give the compiler as much information at compile time as it needs, so that it can optimize, vectorize the code as much as possible. And this actually can make anywhere from a 20 to 30% difference in run times. If the compiler can't know what the runtime definition of a dimension over a element computation is, for example. What this involved in the case of expensive routines that do element local computations, we basically macro expand these at compile time. So in the compiled code, we actually, in the executable, there's actually a third order, fourth order, and fifth order version of these subroutines that we can call. And those are all compiled with the loop ranges over the elements, all specified at compile time. So showing the operational requirements again, I've talked about this before. We have to do 8-kilometer global resolution at 10 minutes before forecast day or better, basically 144 times faster than computer time. We want to be under 50,000 cores. The test workload that we came up with for now, we're going to do larger benchmarks later when we have access to the full machines. But right now we're doing single node performance benchmarks. So that's basically a best case. It doesn't factor in interprocessor communication. The test workload that we used puts 8 columns of spectral elements, vertical columns of spectral elements on each core. And that way we can normalize over different platforms. It doesn't matter how many cores a particular node has. The workload is 8 spectral elements per core, and that basically represents what one core would see computing one of these, computing as part of this 8-kilometer, 35,000 core operational run. We tested 2 systems. Courtesy of Intel, we had access to a Cascade Lake 8268 that has 24 cores per socket for a total of 48 cores on the node. And then through the Computational Fluid Dynamics Laboratory at NRLDC, we had access to an EPIC Rome node, a 7702, each socket 64 cores, so 128 cores total. But again, the number of cores on each node doesn't matter. We engineered the workload, so each core has 8 spectral elements per core. First tested the original code, the one we started with, on this workload and on these architectures, these platforms. And that was 89 seconds per forecast hour, which is 40 times the elapsed time, which is about a quarter of the speed that we actually need to run operationally in a couple of years. I have to admit, in the last couple of years, last couple of weeks, when I did this comparison, I was kind of dreading seeing what this new refactored code would do. We're calling it Neptune 1.0.0. And I'm thinking, wow, a whole year's work of my time and the Navy's money, gosh, it better be faster. And well, it is. About twice as fast. This was 47 seconds per forecast hour, about 76 times elapsed time. That's still only half of what we need. So our work's not done yet. So I've got slides coming up to talk about where we're going with that. Let me have a couple observations about that result, though. First of all, people are generally interested in comparing architectures and how they do on a particular benchmark. In this case, how does the Rome do relative to the Xeon, given that the Rome has higher bandwidth and more cores? Well, on a core for core basis, and for this benchmark, the Xeon Cascade Lake and the Epic Rome were about the same on a core for core basis. Socket for socket, partly because it just has more cores, the Rome was 2.25 times more capable, but it has about the same nominal cost, at least based on list price, and also the same power draw, at least nominal power draw. But we get away with fewer nodes, fewer MPI tasks, and by surface to volume arguments, less network pressure using the Epic Rome. Our allocation that we'd require to do operational forecasting on this new Navy machine would be about the same amount of core hours, but we'll use less nodes using the Epic Rome processors. Now, looking at this in terms of what our requirements are for operational forecast speed, the single node timings, as I said before, this is an upper bound on performance. We still have to factor in communication cost, and also this is dry dynamics. So we haven't added physics yet. Physics, we estimate, will add about a 20 to 25% increase to the cost of these runs. In any case, for dry dynamics, the times are 2.25 times too long on either of the architectures. For the 8-kilometer resolution, we'd require a minimum of 84,000 cores on this new Navy machine. Our upper threshold is 50,000, and we want to get down to 35,000 cores. So the work ahead, computational optimizations. I'm going to show you some work we've done to do compact implementations of the Laypack routines. Just the ad hoc things that you always do when you're analyzing code, use profiles, in this case vTune and Intel's Advisor, to find and address hotspots. There was a first touch NUMA optimization that we came up with that actually has the biggest effect when you're running on large numbers of threads as opposed to the large numbers of MPI tasks on a node. Work on the GPUs, Chris Kung, who's now at NASA Goddard, got us started with some of the transformations to adapt the Neptune code to GPUs using OpenACC. And we need to look at reduced precision. I was really interested in Steve Thomas's talk yesterday, where he showed the reduced precision GMRes formulation and results. We use GMRes. I think that could be a win for us too. I'm also interested in Peter Dubin's talk coming up on reduced precision. Computationally, I'd have to say we're probably getting close to diminishing returns. There's probably still some improvements we can get with additional work, but we're now looking at having to move toward algorithmic enhancements. One of those would be to come up with a hybrid direct or iterative, combination direct iterative approach to the vertically implicit part of the solver. The current option right now, we can either run a direct solver or we can run iterative, and each has advantages. The direct takes longer, but there's one iteration, or there's no iterations. The iterative solver is actually faster, but we expect once we start looking at real data, the iteration count will increase. The hybrid approach would every once in a while recompute the A matrix, redecompose the A matrix, but then between those times do an iterative solve. Until the number of iterations started to get up too high, and then we go back and recompute the A matrix. Greg Rainwater in our group is looking at exponential time integrators, and that's all I can say about that at all. And Kevin Viner in our group is working on the static mesh refinement. So these compact Laypack routines, Intel has a number of these implemented. The idea is applications often have to compute a lot of small matrices, and in the MKL routine, in the MKL library, there's an advantage to being able to do these as a vector. If you can do multiple of these matrices at the same time, and then you can vectorize inside the MKL library. The idea would be that each of these small matrices has to have the matrix index as the innermost index in what you pass down to these routines. Well, that sounds an awful lot like what we did with our element storage. The Neptune's EPX data and loop layout is basically element innermost. We extended the NetLive versions, since we can get source code, for the two routines that this DGB-TRF actually does the LU decomposition, and the DGB-TRS does the solve using that decomposition. And then there are a number of Laypack routines that those two routines call. So we went and we took those and added a V in front of the names, and then pushed the loop over the multiple elements being passed in down into the routines, and then vectorize over those inside the routines. The effect on the way we call these is originally with the Laypack version, we have to have a loop over the elements, and then call for each column, we call the DGB-TRF separately. We can change that to VDGB-TRF and call that en masse by passing it the first element index and the last element index. And then down inside, it actually vectorizes over these arrays. Notice we're not actually having to pass Fortran subranges. So one of the things that does for us is it avoids the copy in and copy out of temporary array arguments. And the other improvement comes simply from the fact that we're vectorizing down inside Laypack. This turned out to be twice as fast using our compact implementations of Laypack. I suspect the main reason for that is, in fact, I'm sure the main reason for that is that we're avoiding copy in and copy out of these temporary arrays that because we're passing in subranges, the compiler's having to copy around these calls. We did offer these back to Intel, no nibbles at this point, but you can have them if you want. The GPO porting, we have a little bit of a breathing room because the Navy's next HPC system is CPU based, that EPROM system. But there are a lot of systems out there, and we have a lot of work to do. We'd like to be able to make efficient use of GPU resources if we can get access to them. Our programming model is the biggest worry right now. I think we've architected the data structures and the loops correctly so that we can switch between vector and GPU threads. The problem is that the OpenMP 4.5 and 5 standards specify the type-bound procedures will be supported, but it's become clear that NVIDIA's plans, at least for OpenMP, don't include supporting those parts of the full OpenMP standards. The reason I was given is that they involve pointers to functions, and I guess that's problematic on a GPU. We need to test this on some of the other compilers. We don't know yet about the IBM, Cray, or Intel compilers. Intel is unlikely to support other than their own GPUs with OpenMP and Fortran. Cray right now is having a little trouble just parsing and generating code for regular Fortran 2000X. We've supplied some bug reports, and those are in the process of being fixed. I don't have access to an IBM compiler yet, working on that. So for now, we do have part of the diffusion model ported to GPU. That's the diffusion kernel in the refactored code that Chris Kung put together. We took apart all the nice object-oriented stuff and have a non-type-bound procedure implementation. Testing that on a V100, it's 2.2 times faster than 32 cores of a dual Skylake on the test workload that we tested. In terms of ad hoc performance measurement, this is a roofline plot that the Intel Advisor tool produced on a recent code. I don't quite have the clutch for getting Intel Advisor roofline plots on multiple MPI tasks. So this is all OpenMP parallelism on 96 threads, I think, which is still useful for comparing different parts of the code. The red spots are computationally hot spots, so you know where to focus on. This is one of those vectorized compact Laypack routines that we did. It takes up a lot of runtime, but it's also running probably about as fast as we're ever going to get it to run. In the course of doing this, I also noticed this one down in the lower left. It's not very computationally intense, and it's certainly not performing very well. So what exactly was this? Well, it turns out it's the pivot routine that's part of the LU decomposition. So we addressed that first of all by just, we hardly ever have zeros or very small numbers at the pivot points. So we just put in a test. If there aren't zeros, if it's not smaller than an epsilon, don't pivot. That got rid of some of that. But the other part of this, and it applies to other parts of the code for threading efficiency, is the reason this is so bad is it's a first touch problem. Each of the element blocks or column blocks was allocating its array in a single threaded part of the code, so that the A array, the matrix, was all going to the same NUMA region. Fix that by allocating and initializing that array in a threaded part of the code, and basically that, oops, wrong way. That goes away. It's not shown here, but trust me, it's not there. And we actually increased the performance from about 40 gigaflops to 80 gigaflops, which is still kind of pitiful compared to percentage of peak. It's about 2%. So summarizing and wrapping up, I described the requirements for and results of a year-long software refactoring effort. We got a 2 times improvement, but we need another 2x somewhere to meet IOC. As I said, these are best case single node benchmarks. We have to test on larger configurations of Narwhal once we get early access. So the wildcards would be, how much are we paying for communication? And what are we going to do about directive-based GPU programming on Fortran? Do we have to take out all the type-bound procedures? That's in active discussion. Working towards IOC, we have to add physics. We're going to use the NOAA Common Community Physics package. We're working with the JEDI group on data assimilation, putting Neptune in the JEDI framework. Coupling to HICOM, CICE, and WaveWatch 3 for the Navy ESPC is going to be under NUOPSI. And we're also working on coupling to a thermospheric model and high altitude physics for a space weather application at NRLDC. And that's what I have. How do I get you guys back here now? Okay, so I assume I read these and then answer them. I hope you all can hear me. I'm not getting anything through the headphones. So what drove the decision not to use Fortran 2000 O and O inheritance, but use your own pointers to access parent classes? No good reason. That's a good idea. We could take a look at that, especially if that gets us around any of these OpenMP problems that we're having. I don't have a ready answer for that question. Matt asks, do you think OpenMP unified shared memory will alleviate some of the modern Fortran worries in multiple memory spaces? Yes, almost certainly. And in fact, we're counting on MPI Direct to help with the MPI communication on GPUs. And let's see, can the compiler inline type-bound procedures to alleviate the function pointer issues? That's, I'm sure it could, but that still leaves us with the question of how do we access them through our types? I don't think the issue is inlining. You're referring to what I said about the calling functional pointers through the OpenMP, and this was an objection that was given to me by the PGI technical person, and he says, well, we can't do it because we can't do functional pointers. I don't know. Maybe I could go back to them with that and say, you know, well, what about inlining these things? And I'll see what they say. My impression was that they're going to be pretty stubborn about it. They've had like 2 years. This was announced, and OpenMP 4.5 and 5 were out there for 2 years, and we programmed based on what the standard said. And now all of a sudden, we're finding out that down at the technical level, there seems to be a disconnect between what the vendors are saying and what the technical people are saying. So I get the impression that there's a lot of issues here that probably aren't even technical. but that's a good suggestion. Thanks for raising that, Matt. I'll bring that up with them.